As Jason kept like so nicely repeating, like everyone here is so young. I do not have that privilege. I am the oldest one here, so um, here is my presentation. It's an overview on predicting student exam scores using through physiological signals. So I think that this paper that we that we wrote was kind of our first major achievement as like IFCON as a whole. We had like a small team of 3 with Elliot, Sean, and me, led by our amazing leader Sam. And so when we initially had this like the idea of writing a paper, and Sam kind of presented it to us, we had to like go through these 3 steps. So the first was conception, analysis, and completion. Conception, what we had to do, what we wanted to do. Analysis was, what we wanted to find using like the initial ideas that we formulated. And then the completion would be formatting our conclusions and the actual paper, as well as submitting it for an attempted publication. So the beginning of the paper, I think the biggest idea that we had to formulate was that we wanted to have an interesting and unique perspective that we could provide to the community, because that when we're writing scientific papers, that we don't just do this for like machine learning practice or coding practice. It's that we want to have an impact on society, as well as kind of learn something more about our community. And it kind of, we kept asking ourselves, like the whole team, and Sam kept pushing us, like, what can we do? What interesting perspectives can we have through our code? So in our team, I think what our issue is that we kind of wanted to combine both machine learning as well as our own interests into this kind of subsection, and to find our own like small little like niche where we could kind of thrive and have like an impact through the paper, because obviously we're competing against like PhDs, and we're competing against like professionals who know so much more than us and know so much more about machine learning, is that we had to find our own unique perspective on it. And what we decided to do was a wearable exam stress data set for predicting cognitive performance in real-world settings. Basically, stressful tests. I think that's what a lot of high schoolers know about. This was a study from the University of Houston on physiological stress in real-world scenarios, more specifically focusing on skin conductance measurements. So for example, like skin temperature or like blood pressure. So our initial hypothesis was that we would be able to clearly form a correlation to attribute physiological stress signals to real-world academic performance. We thought that there could be an ideal kind of flow state between the amount of like tension and stress in our bodies to the amount of academic performance, or the grade that was an outcome to our test. And as we started this process, the initial data sets collected contained 7 different measurements: EDA, heart rate, blood volume, skin temperature, heartbeat interval, and accelerometer data across 3 exams: midterm, final, and then or like first midterm, second midterm, and then a final. And this was and then 10 students were collected across these 3 tests. So our first step, we had to narrow down what we wanted to use for our information. We decided to use EDA, heart rate, and skin conductance levels, just because we wanted easier numeric values to use for our machine learning classifiers. And then once we started kind of individually looking at these measurements, we found that each individual file contained about 23,000 to 50,000 values, which is kind of a lot. So this was why we decided to use this specific data set and this specific study for our purposes, is because machine learning classifiers would be perfect for this, because it could serve as a sample set and a training set that we could input values and hopefully get expected outcomes out of. So the initial step after cleaning up the data sets is that we had to analyze the data and kind of see what we needed to do for like further completion of our paper. And we first ran into issues with variance, outliers, and overall organization. As you can see, like the first and second graphs, it's kind of hard to see what's happening with this information. And as Mr. Lee said, like visualization is super important. with large data sets because we don't, as humans, we don't understand the significance and like kind of the magnitude that each individual file has. So by looking at visualizations, we can understand that that there are certain variables and peaks, or maybe some unpredictable and sudden drop-offs in the measurements that we need to account for. Otherwise, if we just use the information as it was, then our machine learning classifiers could be trained like incorrectly and inefficiently. So upon deeper inspection, we saw that there were clear differences in between the individual subjects. As you can see, like subject 3 on the highest had a resting heart rate, or an active heart rate of around 140 BPM, while other students kind of hovered around like 80 to 100. And we wanted to see if this was because of individual differences, or if there was like a certain sweet spot or a certain value that could result in the best, that generally resulted in the best academic performance. And then, so this is subject 8, his EDA files. As you can notice, like with the final exam, we see that there's like these really sudden drop-offs in the graph, and these represent like the outliers or like kind of unrealistic drop-offs in the information that we kind of attributed to like miscalculation or mismeasurement due to the measuring device or some other variables like the temperature of the room or the humidity of the room that could be interfering with the actual values. Midterm 2 looks a lot better than midterm 1 or or the final. And going further upon this, we had to do data normalization because of these individual outliers and and these like drop-offs, and we wanted to normalize the information so that we could better train our classifiers for better results. So z-score normalization, basic like statistics, and a trick that many data scientists use to get better information. And as you can see now in the graph, after the normalization, it's centered around a mean of 0 with standard deviations of like -3 to 3. And we can see that the information is a lot more centered and close together. So we saw that, and so I did this to all of the data sets that we're going to use. And after doing that, we got better information and better values to use for our classifiers. Now, for our analysis, the actual machine learning part of it, the actual classifiers that we used, as you can see on the chart, this is kind of basically like, this is an outline of what happens exactly in the process. We have the physiological behaviors, the 3 sample sets per subject. We put it into a classifier model, and after training it through half of the sample set, then we get predicted test scores, which we can compare to the actual test scores. And through training the information, we had a 10-fold cross-validation, 10 times, which kind of made up for the small sample set that we had. And throughout this entire process, we assumed that having better data would have better results. So for the classifiers we used 4 main machine learning classifiers: random forest, SGD machine learning, and k-nearest neighbors classifier, as depicted on the slideshow right now. And then for our conclusions, now what? For the results, as you can see on our ROC-AUC graph, the black dotted line represents a random like guessing metric, so a 0.5. So yes or no, I'm guessing if this guy is getting good grades or bad grades. And as you can see, the random forest and the SGD curve, or SGD like predictions, were very close to the random, to random guessing. And the further and higher away the line is for the classifier, the better it did on predictions. And for us, our best performing classifier was the KNN, which had a curve of 0.81. So that meant that 81% of the time it was accurate. For limitations and further improvements of our paper, we do acknowledge that we had a small sample size. It was only 10 subjects with 3 measurements for each. And we kind of tried to supplement this by repeating the process and analyzing our data as much as we could to create a better sample set and data set. And also kind of another limitation that we had from using another data set was that we had less control over the variables that were included with this. We couldn't account for if each student was in the same spot every time, if they had different variables that we could account for, like, like their stress or their like test preparedness. Now, for the creation and submission of the paper, we just submitted to the EMBS society, and we're going to be waiting for our publication, and if it does, we'll be going to Australia over the summer to present it. And kind of looking over hindsight, I wish that we went into this paper initially wanting to understand why and how that stress could affect academic performance levels. And we didn't really accomplish this because we didn't really identify if there was a perfect sweet spot that we could try to emulate ourselves. Having an optimal heart rate, having an optimal skin temperature for the best results academically, that this could be a factor that we didn't account for when we're just taking our tests normally. But that's going to be something that we want to improve further and maybe work on further. And we're hoping that small changes have the big impact, that by modifying a little bit of the data or improving some more of the classifiers, that we can get better results. So thank you.
Thank you so much for the impressive presentation, and you're still so young. So yeah. So do you have any question?
So you picked 3 out of the 7 to train your machine learning algorithm with. So I'm curious, what were the results of the correlations if you ever shared them?
Are you asking the correlation between the different measurements?
So I'm curious because the goal of the study was to predict test scores using the 3 factors. So were the 3 factors useful? Was there a positive correlation?
Yeah. So the machine learning algorithm, this is kind of what I wanted to address, is that it didn't really address. All it did was try to find trends between the different data, the different measurements that we had, right? So if someone could have a high heart rate with a comparatively low skin temperature, and someone else could have a low heart rate with a comparatively high skin temperature. And what we kind of did was we normalized the data so that we could have means between each measurement, and that we could give these significant values, like a value of 0 or 0.5, depending on how high they were compared across the 3 different files. So I think what you're asking is did we find a correlation? Was high heart rate better for your academic performance? Is you'll see when we publish our paper.
I see.
Alright, so you mentioned how this was a group project. What was your role, or did you guys all do the same thing?
Yeah. So as you can see, the data part was kind of a bigger part of my presentation. I worked on the data part, so we all did our own individual research for the data set. We decided on it, and then I focused on extracting all the data that we had, and then Sam obviously helped with cleaning it and then reformatting it into stuff that was better to use. And then I sent this over to Elliot, who used his own, who was modifying his the classifiers that we used to get better results. And then Sean kind of accumulated all of the results and then kind of created what we had.
Since you showed in the beginning that some users have very different physiological signals, heart rate or whatnot, I'm wondering if instead of trying to kind of put them in the same space by Z-normalization, would it rather make sense to train a personalized model for each person? And is that a good idea, or does that hurt the performance?
Yeah, so actually, I did attempt to do that, just because I thought it would be better if we compared, because obviously we have different body temperatures, so a high spike in someone's body temperature could be comparatively normal to me, while me having a relatively very slow day could be considered a fast day for other people. But what we did notice is that when we were doing individual, or what I noticed is what we were doing individual comparisons, and only across the 3 sets and the 3 tests and then the information, is that obviously we had too little information to kind of form like good, to find like good data set off. And when we did input this into algorithms ourselves, like the results were, I would say they were kind of overfitted a little bit, that they were giving us like results that were either too good or too bad, and it kind of didn't make sense for an academic like paper that we wanted to write. But I think like if we could replicate this study again, and we could use this information like, and we could actually kind of control more of the information, have more, just more like data and more subjects overall, then that could be a, that could be like an avenue we go down. And kind of elaborating further is that we do have like the average of the 10 subjects, so we could compare individuals to the average of all the characters of all like of our mean, but like we wanted to elaborate on that further like next time.
Yeah, so can I ask you a question?
Yeah.
So what you want to predict was exam scores, right?
Yeah.
And as a method, you use some classifiers. So how do you map these classes of the scores and actual exam scores?
Yeah, so I think ideally we would input someone's values. This guy had a range of 80 to 90 heart BPM, and his skin was kind of high, and we predicted that he would get like an 85%. And in reality, he got an 87%. So that's what we wanted to do. But in reality, what we did was we classified through bad and good scores of having like the cutoff was like a 70% or like a 80%. And then, so then we would predict if they were higher than this score or lower than this score. And then as we have their actual test scores, then we can actually compare like high or low to that. I don't know if that answered your question.
Yeah, that answers my question. Any other question from the audience? Okay, so if you have no more questions, then thank you so much for